All right, let's get started. All right, so remember this week you need to meet with, you and your partner, if you have one, need to meet with the TA for 15 minutes to show some progress on the assignment, the final assignment, and you make an appointment to do that. And you need to be in a group to do that. So be sure to take care of that this week. Are there any questions or problems before we go any further? Yeah.
So I have a question about like the participant countdown timer. So trying to like put in an alien ship with like a delay and it changes directions, and then when I do the participant countdown timer, when it expires, it sets new change in direction, and then it builds a new participant countdown timer. But every time it does that, it basically pauses the game for however long I have it set for. I'm just not entirely too sure why.
Well, sort of trailed off at the end so you couldn't hear, but bottom line is question about the participant countdown timer. I think I'll just need to see what you're doing to
Okay.
figure out what's going on. Any other questions? Yeah?
In the project description, you mentioned that the start code has a lot of little comments on every little bit of code, and you expected a similar level of commenting. Should we have about in-code comments about every line?
When I said some amount of commenting, I meant for the Java doc. I comment code inline more than most people do. Part of that is just because I figure students are reading the code. So yeah, you don't have to do the inline code commenting like that. Any other questions? Okay, this week I'm going to give you a taste of some other topics in computer science. And actually, these are things that you'll be seeing in more detail, much more detail in 2420. Just think of this as sort of a preview of 2420. And one major topic in 2420 is algorithms. And one major algorithm that is important to be able to deal with is sorting. So today we're going to talk about a few sorting algorithms. So the sorting problem is just given a collection of things, an array of things, to put them in order according to some ordering, numerical ordering or what have you. And it shows up all the time. So who could tell me a few ways, a few places where applications that you have used depend on sorting? Yep.
Could that be like using a list to find the largest of something? Like you'd be sorting through the list, right?
Yeah, but what I want is some program that you've used, not one you've written or that I've written, just some program you use on a daily basis even. Yeah? Okay, how does Google sort things?
Well, you type in a specific thing and it goes through, or a specific website or something you want to search, and it'll go through and search either alphabetically or numerically or whatever it is, but it's sorting.
Okay, but what I thought we were going to see, when he said Google, what I thought he was going to say the sort was, it's sort of sorted by Google's PageRank, right? When it gives you back a list of links, it puts the ones it thinks are most important, most useful at the top. So that's sorting. And it has to sort the results. What's another example? Yeah.
Like the file explorer problem. Programs on our computer can sort files by alphabet, file size, descent.
Okay, so that's another good example. You use the file explorer on a computer. You can sort in various ways, depending on you want to see the newest file or the biggest file or the one first in alphabetical order. Yeah.
Probably just like a more simpler example, but when you're in Excel, you have to like sort just like list numbers.
So when you're using a spreadsheet, you often sort columns. So that's a few examples. And the thing about sorting, if you're sorting a few things, like these 7 things, these 8 things, about any algorithm will do. But when you're sorting large sets of things, millions of elements or hundreds of thousands of elements even, there can be a huge difference in the running time between 2 otherwise correct algorithms. So let's start here with these numbers. would it be any big trick to sort these? Who could tell me how to sort these into ascending order? Yeah?
You could check. You could pick like one. You could pick like one as your starting point, and then you check whether one is greater than the next.
Okay,
value,
so
and then switch.
all right, so he's describing a sort of sorting algorithm to me, but there's actually an easier way to deal with this. This is simpler than what we think of as the sorting problem. What's simple about this? Well, who could tell me how to sort this with the fewest moves? Yeah?
I mean, this is just because we can see all the cards right across, we know what order they should do, we just move.
Right. You can see all the numbers. You can look at the numbers and make a plan. And it's easy to say, okay, let's swap the 0 and the 1. And then let's take the 2 and put it here. 3, move the 4, the 5, and the 6 over. And put the 7, and I'm done. Okay? But that's just because I could take it all in at once and make a plan. And there were only 7 of them. So it wasn't too hard. I don't know what I'm doing here. So I'm going to make it more realistic. This is more like what a program has to do. There we go. So now, that kind of makes it harder, doesn't it, to have to sort them. I'm going to give these index numbers here. Now let's sort these. The only question you can ask me is to compare two cards. Okay? And I'll tell you which is smaller. So you might ask me, compare 3 and 4, which is smaller? And I'll tell you which is smaller. That's all I'll do for you. And let's see if we can sort them. Okay? What's your strategy?
First, check whether 0 or 1 is larger.
Well, I'll tell you which is smaller. So of these two here,
Yes.
this one's smaller.
Okay, 2 and 3.
Okay, so you compared the first two,
Yes.
2 and 3,
Mm-hmm.
smaller.
2 is smaller of the 2?
2 is smaller than 3.
Of the 3.
No, I can only compare 2 things.
Okay, sorry. Okay, so now we know that 0 and 2 are the larger of the 2. Is 0 or 2 smaller?
0 or 2?
Yes.
2 is smaller.
Okay, so then 2 should be moved to the front.
So I should swap 2 and 0?
Sure.
Okay, so why don't we stop there and tell me your strategy?
Split it up into a binary tree and then merge them back together
Okay.
as you go through it.
Okay. So basically what I think what he just tried to do was, and succeeded in doing, was finding the smallest of these 4. Right? He found the smallest of these 2, the smallest of those 2, and then the smaller of the 2 smaller ones. So we've made some progress. Let's try a different idea.
Couldn't you do like a for loop where you compare 0 and 1, like one index to the one next to it, and see which one's smaller? If the first one is smaller, then you keep them the same. If the second one is smaller, then you flip them.
And then what do we do next?
And then after that, you move on to the next one, like 1 and 2.
Okay.
If 2 is smaller than 1, then you flip those.
Okay. All right, so that has the advantage. It's a little easier to describe than what you did. So let's try it. So you'd say compare these 2. This is smaller, so leave them alone, right?
Yeah.
Okay. I compare those 2, and this one is smaller. What should I do?
Flip them.
Flip them. Then I'm going to compare these 2, and that's smaller, so leave them. I compare these 2. This one is smaller, so I'll flip them. These 2. This one is smaller. These 2. This guy is smaller. And these 2. This one is smaller. Are we done?
Nope.
Okay? what can you say about the arrangement of these things right now? Being able to not see the back. Yeah?
The max value is at the end.
Okay, he's saying that the max value, which is 7, is at the end. How do we know that?
We compared it to every other one in the list.
Yeah, we started with these two. We looked at every card, and when a card was bigger, we moved it to the right. So the biggest one has to be at the right, and in fact it is. Okay? So how could we finish?
We have to repeat the loop.
Repeat, but we could do a little shortcut here. Do we need to look at every card now? Well, is this guaranteed to be the smallest? It's not the smallest, because we're moving everything. You know, if the smallest one happened to be here, it could only move by one spot to the left. Okay, that's because of the direction we're going. But we can repeat the process on these cards and not bother with that one because it's guaranteed to be in the right spot. So we could do that again, and after that, what would be true? That would be in the right spot. So you can see we repeat this enough times, and eventually it's done. Anyone know what that algorithm is called?
Bubble sort.
Bubble sort. So in bubble sort, you compare adjacent elements and swap them, and you make multiple passes until you're done, until either you've done enough passes or until nothing gets swapped. Bubble sort is just about the worst sorting algorithm possible. It's easy to explain, but it's, I guess possible is the wrong word. It's one of the worst that has a name. But it's really inefficient. Let's try a different one. This is one called selection sort. The idea behind selection sort is we start here and we scan through the entire array looking for the smallest element. And when we find the smallest element, we swap it with whatever was in the first location. Okay? And repeat. So let's try that out. I compare these two. This one is smaller. Okay? So now I compare this one to that one. This one is still smaller. This is still my champion, so I'll compare this one to that one. This is still smaller. This one to that one. That one is smaller. I compare this to that, this to that, this to that. This is the smallest, so I swap them. So I found the smallest one in the array, and it turns out that I did it wrong. The number's written on the back. I read it wrong, so yeah, I should have done 0. Now, how do we finish this up?
Do the same thing except you read out the first index.
Right. This is in the right spot, so we'll just ignore it. We just do the same thing. We search through this part of the array for the smallest thing, and we swap. And now this is in the right spot. And you just repeat that until you get everything into its proper location. So you see, so far I've got 0 and 1. And we can do this just by comparing two elements at a time. So that's selection sort. Okay? Let's look at selection sort in more detail. Okay, so this is an animator. It'll animate some sorting algorithms for us. And I'm going to set the size to something smaller like 8. So the first thing you need to tell you is how to interpret that. So what you're looking at is an array of size 8, the 8 elements, 0 through 7, just like we had up there. Think of this axis here as being array indexes. So this first black box is in index 0, and then the next one is in index 1, and then index 2, and so on. And then think of the horizontal axis as being the magnitude, so that this level is level 0, this is level 1, this is level 2, and so on. So what you have is element 0 is in location 0, element 1 is in location 1, and so on. So what can you say about the array at this point? It's sorted. Now, what I can do is I can put it in reverse order. What would a reverse sorted array look like? It'd just be a line in the other direction. So that's what the array looks like reverse sorted. And I can just permute them. Okay? So when I permute them, what element is in the first location of the array? So the top is 7, the bottom is 0. So we got 5, 7, 6, 2, 3, 0, 1, 4. Okay? Now, it's not important to be able to glance at it and tell the magnitude. It's sufficient to know that, okay, that's scrambled up. There'll only be one box in each column, because the array can only have one thing in a column. There'll only be one thing in each row, because every element has a different magnitude. So when it's all scrambled up, it looks like that. When it's ordered, it looks like this. When it's reverse ordered, it looks like that. So let's sort this using selection sort as our algorithm. Now I'm just going to step through it. Now what's the first thing that selection sort will do? What's the first comparison it will make?
0 and 1.
Okay, it will compare the first two elements, index 0 and index 1. So when I click step, it shows me which two it's comparing. So it's comparing those two, and the one in column 0 is the smallest. So which one will it compare? Which two will it compare next?
1, 2, 0, and 2.
The one on the left, which is the smallest we've seen so far, and the one in column 2. So when I click step again, now it's comparing those two. Column 0 is still the champion, so now it'll compare those two. Now what will happen? We've got a new champion, so we'll compare it to the one next to it. It's still smallest, so we'll compare to that one. That one is smallest, so it'll compare to that and compare to that. So we've just made a sweep through. We've done all the comparisons, and the winner is the one in index 0. And so what will we do with this guy? What will change about my image? Okay, we're going to exchange with the thing in column 0. So this one here, the one at the bottom, is going to go over to here. The one up here is going to go to this column. We're just swapping the elements in the array. So I'll click step again, and you'll see them switch. So now we've moved that guy there, and the one that was originally in column 0 is up there. Now we're going to do another pass, same thing. We leave that thing where it is. We compare those two. We have a current champion. We compare that. That's the new smallest. So that comparison, that comparison, that comparison, a new champion, a final comparison, and then the swap. Then we make another pass through what's left of the array. So we do those comparisons, and then we take the smallest one and put it in the right spot. Another pass. Swap. Another pass. Swap. Another pass. Swap. And that final one. So that's what selection sort looks like. Okay? Let me see if there are any questions about it before we look at code for it. Yeah?
So in this case, when it finds the value at, the value is 0, that should be in that first index, why does it keep on going?
Okay. So he's saying, let me permute this again. When it steps along and it finds 0 right here, why does it keep looking? Okay? Fair question. Why does it quit looking? Why doesn't it quit looking, rather? Yeah.
The program doesn't know that this is the smallest value.
Right. Program doesn't know in advance what the smallest value is. We can see it. We know it could quit at this point. But for that matter, why not skip all this stuff and just rearrange you just draw the boxes in ascending order. Okay? That works if you know you're sorting the numbers 0 through 7. So the algorithm is very general. Yeah?
Can we, since we know like the range of values, can we say once you find the 0 value slip?
Well,
there's certain other data sets where you know like what kind of data is going to be in there.
Yeah, well, so if you know something about your data, then there are tricks you can play, such as knowing when you found the smallest one. But in general, what we're studying here are algorithms where all you can do is compare two elements. You can't even tell you've got an element whose value is 0. All you can do is compare. And you don't know in advance what the largest or smallest is. It's like the cards with the back turned. Yeah?
Is there any other more efficient algorithms to arrange them like this that you don't have to have special knowledge about?
Oh, yeah. Yeah. In fact, I'll show you right now. So what I'm going to do now is I'll increase the size. Let's see what's visible. Okay, so that's 256 elements. And I'm going to order them in, I'm going to permute them. And then the computer is so fast that it gets over, I'm going to put a moderate amount of delay. I'm going to artificially slow it down. Every time I do a comparison, I'm just going to pause for 3 milliseconds just so this thing doesn't end right away. And now we're going to sort using the algorithm, which is selection sort. Okay? So what are you seeing here? Why is it building up from the bottom that way? That's just how the algorithm works, right? It finds the smallest, moves it to the next column. Finds the smallest, moves it to the succeeding column. Now, if I hit step here, what can you say? You see, at any point, if you stop selection sort in the middle, there'll be a place you can draw a line, and that line is right here, where everything to the left is in perfect order, right where it needs to be. Everything to the right is still randomly distributed. So you've got a sort of a perfect area and a randomly distributed area. So let's start it up again. And it gradually, the perfectly sorted area grows up and the unsorted area gets smaller. And you'll see the algorithm seem to speed up. So why will that line start to grow faster as we go forward? Comparison. Yeah, each pass goes through a small and small amount of data. Okay? Well, I might be able to wait. I'm tempted to kill it at this point, but it encourages me that it's speeding up. Now, the effect this should have on you is, you should think, yeah, that is not a very fast algorithm. Even though the speed here, selection sort would be fine on 256 elements. I'm throwing in lots of delay, and also the animation takes time. But you just have to take my word for it. It's not a very good algorithm.
30,000 comparisons.
Yeah, you can count how many comparisons have been done. So yeah, it's exceeded 31,000, 32,000 comparisons at this point. Okay.
What happens if you don't have the...
What happens if what?
If there's no delay?
Well, if there's no delay, okay. Yeah, at least it's right, but I'm going to handicap all the algorithms the same way. Now, here's an algorithm called Quicksort. We would think Quicksort would be faster than selection sort. Okay? So there's the speed, still moderate delay. Here's Quicksort in action. Okay? Quite a bit faster. If I put the speed back up to fast and permute them, and we do selection sort, you get that effect. You do Quicksort, you get that effect.
It's quick.
It's quick. Okay? Let me show you another algorithm called Insertion Sort. And I'm going to, so you can look at it, I'll put it on moderate. And yeah, you can see that it has a different characteristic. It looks different in operation than selection sort did. Who can look at what it's doing and figure out what's happening? What's insertion sort doing? Yeah?
Well, every time it finds a new one, it puts it in
place on the line.
Okay, I'm going to stop it there. Yep, so what it's doing is, it starts and says, the first element's okay, it looks at the second element and pushes the second element as far to the left as it'll go. So if we were sorting these numbers here, let me turn around. And scramble a bit. Okay, here's how selection sort works. Leaves that one there. It looks at this one and says, I'm going to push the one as far to the left as it'll go. So the one is smaller than the 6, and that's as far as it'll go. Then what happens with the 7? It's happy there. What about the 5, though, can be pushed all the way past the 7, past the 6, to that spot. The 2 can be pushed past the 7, past the 6, past the 5, into that spot. So what you're seeing up there is every element in turn gets pushed, and you sort of see stuff. That's why the line seems to move to the right. Okay? The 3 would percolate all the way down to here. The 0 at the end would have to go all the way here. So I'll turn this back on. Oh, turn it back on. So one by one, those elements, each of those things is moved down as far down the line as it can go. Sometimes it goes a long way, sometimes a short way. And this one has only done about 7,000 comparisons by this point. So in practice, insertion sort's about twice as fast than selection. Insertion is twice as fast as selection. But it appears to slow down as we go. So I'm going to do it again. I'll do it fast. So here is insertion. And here is selection. Okay? Now I'm not trying to teach you all these algorithms so that you memorize them or anything. I'm just going to show you, I like the pictures. Here's one called shell sort. Okay? So I'm going to put the speed, probably moderate, because shell's pretty fast. So this is shell sort. See if you can just sort of characterize how shell sort works. You can see it's making multiple passes. So what's it doing?
So is it like, we're like narrowing all the comparison options that need to happen?
Yeah, it's a variant of insertion sort, but instead of trying to get perfect the first time, it makes one pass that just gets things close to where they belong in a wide band. Then it goes again and moves them into a narrower band, and it uses narrower and narrower bands until it gets it completed. So let me permute that again. So you can see right now it's just doing a rough sort. And I think it's done about now. Now it's going through and getting them even closer to where they belong. And then again, and then again, and then a final. The final pass really is insertion sort. So if I take the speed to fast, okay, so that's that shell sort. You can compare that with insertion sort. Okay? Here's one called merge sort. This is full speed. Here's it slower. This is pretty much what you were having me do. Now, the problem with the animation here is there's a second array that's not being animated. And when it disappears, everything's being copied to the other array and then copied back. Okay? You have seen Quicksort. Here's heap sort. I really like the way this looks when it's animated. So we'll go moderate. It almost like reverse sorts them, sort of. And then it starts So you sort of got the perfectly sorted line, and the rest of them are sort of ordered backwards the way they need to be. And you play around with this thing enough, you learn some cool things. Oops. Let's start with the array like that. It just seems interesting to me, the difference that you get. Let's try insertion sort that way. I'll speed it up. And let's try selection sort. Okay. So there's just some simple visualizations of sorting algorithms. Yeah?
Is this program available on Canvas for us to...
You know, it will be. I'm in the middle of modifying it. I've been using it since about 1998, and it just stopped working it was deployed on the web, and it just won't work anymore because it's too insecure, so I'm fixing it up. But I'll put it up there for them to see. Yeah, it's just a Java program here. Okay. Any other questions? Or, you know, we're going to think about how to implement these things, but some of them. Yeah?
You know, some of these like better for different things than others, like for sorting numbers rather than letters? Like, or...
Well, all we're assuming about the elements is that you can compare two elements and see which is smaller. Okay? So, yeah, sorting letters versus sorting numbers, there really wouldn't be any difference. One difference, the one that does the fewest moves is selection sort. We're basically, you're seeing all the comparisons that are happening. Selection sort makes a pass and does one swap. Then it makes another pass and does one swap. And all the others do many more swaps than selection sort. So I often say selection sort would be the right way to sort elephants. Because, you know, sort them by weight. You wouldn't want to move them around too much, so you would figure out which is the lightest and put that one in the first stall. And you spend a lot of time comparing, a little time moving. Any other questions? All right, let's think back to selection sort. What would a program, a method for selection sort look like? Yeah?
Would it be like a comparison kind of loop thing where it takes like one number and compares
Okay.
to the next number?
So the pass through, we're looking for the smallest one. What kind of loop would that be? That's an optimization loop. But then you'd have to do that optimization loop multiple times, right? Because it takes multiple passes. So it would be a doubly nested loop. So let's look at my implementation of selection sort right here. I need to make it bigger. Okay. So here's my implementation. I say for, we start with I equals 0. We go up to, but not including the last element. So we're looking at every index except the last one. We don't look at the last one because when we get that far, there's only one element left. It has to be in the right spot. So for each index, what we do is we find what this method do, we'll find the smallest thing in A that occurs at I or to the right of I. So we find the smallest element and whatever, and then we swap it. So if smallest is the index of the smallest element in the rest of the array, we swap it with I. So we search, we start here, we search, we find the smallest, we swap. Then you move your search over by one, you search, find the smallest, you swap. The question is, how would you implement index of smallest? So what index of smallest has to do is, given an array and an index, returns the index of the smallest element in the portion of A beginning at index I. So I would say, okay, starting here, find the index of the smallest element. And what would be returned? What's the index of the smallest element from 2 on over to the end? 7. 7 is the index. And then the next thing we can do is swap 7 and 2. But obviously we already screwed up earlier. Okay? At this point, you ought to be able to write an optimization loop pretty quickly. So do it. Okay? Pretend it's the final exam. And I've just asked you to write this method. You can easily see that on the final exam. So you can write on paper, write on the computer, talk to the person next to you, whatever. See if you can write this method for me. There's the specification right there. Remember, it's an optimization loop. The only trick is you got to keep track of the index of the best so far as opposed to just keeping track of the best so far. Okay, I know most of you aren't done, but at least you've thought about the problem. Who could tell me, sort of describe at a high level, what does the method look like? Yeah?
You need a loop that iterated through the length, iterated through each of the items in the array.
Okay, so, well, not each item in the array. You just need to go from I to the last index. Okay? Because we only care about the portion of the array beginning at index I to the end. So we got to have a for loop that starts at I, call the index variable j. So j needs to go from I to a.length minus 1. Okay, what do we do inside the loop? Yeah?
What you do is if you set the smallest number to be I, it would be if the array at whatever index variable you have is smaller than the smallest number, then the smallest number becomes.
Okay. So basically it's a standard kind of optimization loop. You're just looking through for something smaller than you've seen before. So I'll just expand mine out. Right, let's see what. I said, I didn't use a for loop. I said let index equal I, and then I said while I is less. Okay, so index I really should have called, just to make this easier to understand, I'll call it index of smallest. Okay? So we start off by saying, okay, I is the smallest thing we've seen so far. The index of the smallest thing we've seen so far. And then for every other I, we look and see if a sub I is less than a sub index of smallest, then index of smallest becomes I. As soon as we find something that's smaller, we update the index, and then in the end we return the index. So it's just a textbook optimization loop. Right? So this is the sort of thing that in 2420 they're going to assume, bang, 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 no problem. They want to build more complicated things out of these simple loops. Okay? So that may be something to brush up on before the final and before taking 2420. Any questions about the implementation? Okay, so just to remind you, we have a loop up here, and it keeps getting the index of the smallest element in what's left of the array, and then it swaps it into position. And it does that the right number of times, and that sorts the array. That's what we're seeing in the animation. All right, let's take a break, and we'll do some more sorting comparisons. And the director isn't here. Let's think of another sorting algorithm. So let me mix these up again. So let's describe the algorithm this way. We've got 8 cards to sort. Let's take half of them and go sort them over here using whatever means. So I'll just sort them. So we sort the half of them over here, and then I'll take these and I'll sort them over here. All right, so I've got half the array sorted on the left, half the array sorted on the right. How can I combine them to get an overall sorted array back in the middle of the board? What's an efficient way to combine this set of cards with that set of cards? Both are sorted. Yeah?
Have it determine the lowest value between the two that's currently the lowest in each array, and put that one in the current slot, then find the next one.
Okay. Exactly. We find the lowest element in both arrays, and then we take the lower of those two, put that in the first slot of the new array. Now, how complicated it is to find the lowest one in both arrays? What do we have to do to find the lowest element from both arrays? Does that involve searching? Yeah?
It's already in the first index 0, because they're already been sorted.
Okay. We take advantage of the fact that both of these are sorted. This is the smallest element in that array. This is the smallest one in that array. So we just need to compare 2 elements. We take the 0 and put it here. Now what do we do? We're looking at the card on the left. We look at the 2 right there. We look at the 1 over there. The 1 is smallest. So we put it here. We compare the 2 to the 4. 2 is smaller. We compare 3 to the 4. So this is a pretty efficient algorithm. 4 is the smaller. 4 is smaller than 5. 5 is smaller than 7. 6 is smaller than 7. And finally, we get to a spot where one of the arrays is empty and one isn't. And so we just take the rest of them from the one that's not empty and bring it over. And that's called merge sort. Merge sort. You split your array in half, sort the 2 halves, and then merge them together into the result. Yeah?
So, at one point you were comparing 2 to the
2 to the 4, but what if the 3 was there instead before the 2?
Okay?
What is this?
So in other words, what if it had been like this over here?
Yeah, and then you compare 3 to the 4, and then the 3 would have been there.
Okay. Is that a problem?
You sort of import it.
Right. The point is, the two subarrays, the two side boards, were sorted in advance, so it couldn't have been like this. This was sorted. The 2 had to have come before the 3. So split the 2 halves off, sort them individually, merge the result. That's merge sort. Yeah?
So what sorting algorithm do you use to sort the 2 ones?
Ah! How do we sort the 2 halves? Merge sort. Why not? Yeah, we got it. Merge sort works fine. Right? It sorts arrays, so we recursively use merge sort to sort the subarrays. It's just more recursion.
So to use merge sort, you need 2 arrays, right?
Yeah, I'm actually using 3, but you can do it with 2.
3. So if you start with 1 original one,
Mm-hmm.
where do you go from there? You start with 1 original one.
Well, let's look at the code. Okay. So that's selection sort. Here's merge sort. Okay. Here's the whole algorithm. So there's my sort method. It takes in an array. So the first thing I do is there's a built-in method called copy of range. Basically, I take the elements of A from index 0 to A.length divided by 2. Really, it's A.length divided by 2 minus 1. It's the way the algorithm works, the way that method works. In other words, it copies the first half of A and returns it as an array, and we call that left. And then we copy the right hand of the array, the right side of the array, and into an array right. So now we have left and right, the left and the right subboards. Then I sort the left. Okay? Now, well, I mean, how do we know that'll work? Well, it says right there, sorts A into ascending order. So we call merge sort to do the sort of A, of left. We sort the right. And those calls will split their arrays in half and sort them and combine them. We don't care how it does it. And then after left and right are both sorted, we do the merge operation. Now, why isn't this infinite recursion?
Because it says that A.length is greater than 1.
Right. If A.length is less than 1, is less than or equal to 1, we don't do any of this stuff. What do we do if the length of the array is 1? It's already sorted, right? How can a 1-element array be unsorted? So we don't do anything. And what if the length of A is empty, which can happen? What if the array is empty? There's nothing to sort, so we just return. So when the arrays get small enough, we don't do the recursion. That's the base case. But otherwise, we get 2 chunks. We sort them recursively. I mean, we could right here sort them using selection sort, but that turns out to be a bad idea. It's not as fast. Okay? This is another issue you'll be confronting. I'm sure you're not the only one that's worried about this working. Recursion is something, again, that you'll see in a lot of guises in 2420. Yeah?
So what does the method merge do?
Well, merge does that operation that we were talking about. We have the sorted half on the left board, the sorted half on the right board, and then we combine them into an overall sorted array here. So it takes 2 sorted arrays and merges them into 1 sorted array. So let me show you. Okay? It takes an array left, an array right, and an array to put them in. And basically what this loop does here is it repeatedly compares the first element in left to the first element in right and moves the smaller of those to the destination array. And eventually, one of your subarrays becomes empty. And then we copy all the leftovers from the left array into destination, and all the leftovers from the right array into the destination. Of course, one of those will be empty and no copying will happen. So I'm not too concerned about understanding the details of merge beyond the way I described it on the board. It's just enough to know that that's how merge sort works. It recursively sorts the two halves and then merges the results together. Okay? Let's run the animation on that. Better save that. Here's sorter. We'll bring it up. And I think this is best appreciated by running it. We'll run it at moderate speed. Put a big size up. No, that's not cooperating here. It was all fitting. I'm not sure what's happening. Was I using 256 before? Oh, I see it. It's just scaling only. Okay, so there's the 256. We'll permute them. And again, I'm not animating the two arrays things get copied to. But what you'll see is that you'll see two sorted arrays that get merged into one over and over again. And it will start to be more apparent as the animation goes on. It would be if we were running merge sort. So you can see them get zipped together. Two sorted halves get zipped together. So half the array has been sorted, now the other half is being sorted. You see the merge has happened that does that. And the final merge. They get all copied over. This is working a little bit differently. What it's doing is it's merging them over to somewhere and then copying them back. The copying is happening in a different order than I described. That's merge sort. Any questions about how it works? We just touched the surface, and I'm sure they'll spend plenty of time in 2420 on merge sort because it's such an interesting algorithm. Well, let me pose this question to you. Here we have selection sort, which works with two nested loops. And then we have merge sort, which uses recursion and a merge loop. How do you think their performance compares? Would you expect one to be way faster than the other? About the same? What do you think? Is recursion bad? Recursion too slow to use in practice? Anyone have an opinion? You have an opinion. Great.
Merge sort is much faster than selection sort.
Okay. You just know that.
Yes.
Okay.
I'm not going to get into the technical reasons behind
Okay.
it. It's much faster.
All right. So he feels it's much faster. And in fact, let's see. Let's make the size 512. Make sure the speed is fast. Permute it. Let's just see on our simulation here. We will do selection sort. I don't know, that's maybe 10 seconds. Now let's try merge sort. Okay. Now that's, again, that's artificial because there's just the animation's taking all the time, not the algorithm. So let's try something else. Well, that's a good point. You can look at the number of comparisons because when you analyze, another thing you learn in 2420 is to take these algorithms and learn how to predict how they'll perform. That's called algorithm analysis. And when you analyze sorting algorithms, it turns out it amounts to counting the comparisons. So you see merge sort did 3,900, almost just short of 4,000 comparisons when it was operating. I didn't notice, let's do the other one here now. So 4,000 comparisons by merge sort. 130,000 comparisons for selection sort. That seems like that merge sort ought to be way faster. So let's do this. Here I have a method called sort timer. Something else you'll do in 2420 is you'll not just analyze algorithms mathematically, you'll learn how to time them. So analyze them experimentally. This wouldn't get you a passing grade in 2420, this timing code. It's not a very careful, scientists, when they do lab work, they need to be careful to control for all kinds of things. Same thing is true of timing. This is just a quick and dirty way to time how long things take, but you'll learn better procedures. So all I'm doing is I'm creating a sequence. I start by creating a 10,000 element array, sorting it with selection sort, and then I print out how long it took. There's a method that I can tell how many nanoseconds have passed. So I see how many nanoseconds have passed beforehand, how many after. This is nanoseconds since 1970. And then I do a division to figure out how long it took in milliseconds, in seconds. Okay? And each time through the loop, I double the length of the array. So I do a 10,000 element array, then a 20,000, then a 40,000, then an 80,000, and so on. So let's run this and see how long selection sort takes. Hold on. Okay, so 10,000, we're up to 80,000. 80,000 took 2 seconds. Then it took 160,000 took 9 seconds. I'll predict the next one will take about 36 seconds. Because theory predicts that when you double the length of the array, the time selection sort takes should quadruple. Roughly. But I'm not measuring very accurately. And I'm not willing to wait longer than 36 seconds. There we go. Now, in the right column, what you see is the ratio. So that 2.93 says that the second timing for 20,000 was 2.93 times bigger than the first timing. So that 0.1507 is 2.93 times bigger than 0.0515. And you can see it settling down into that being 4 times longer. So just remember this, that we've been here for doing this for about a minute, and we got up to 320,000, and then I got too impatient and I killed it. But 320,000 element array took 36 seconds to sort with selection sort. So now let's comment out selection sort, and let's time merge sort. Okay? Before I could turn around, we're done. So 5 million. 5.1 million took 1.1 seconds. How long would selection sort have taken? What? This one was 36 seconds. This one would have been 4 times longer. 4 times longer, 4 times longer, 4 times longer. We're talking hours.
About 2 hours.
Okay. About 2 hours. So if you're tempted to think that, one way of sorting is just as good as the next way, that just ain't true. Selection sort just can't keep up. You'd be really bummed if you had a million element spreadsheet and you had to wait 2 hours for it to sort. Because the person implemented the web page didn't take, the spreadsheet didn't take 2420. Now, that's my merge sort, and I wrote it. There are tricks you can do to make these things more efficient. I just tried to make it so that you could look at the code and understand it. So we're going to look at the built-in sort in Java. So let's just remember that my merge sort took 1.1 seconds at the end there. Let's see how long Java's takes. Okay? So what can you say about Java's? It's better. It's about twice as fast across the board. Okay? So Java's sort is better engineered than mine, so it's twice as fast. But selection sort, no matter how carefully you engineered selection sort, it couldn't compete with my simple little merge sort. It would just be way, way, way slower once the arrays get big at all. Yeah?
Is there a situation where selection sort would be better than merge sort? With numbers.
In theory, selection sort might win for really small arrays. But the thing is, any algorithm you can think of is going to be fast enough for really small arrays. Where you care about speed is when the arrays get big.
So everyone wants to know what Java uses.
Java uses
Combination?
it's a combination. Yeah, it's based on Quicksort, but it's got some ideas of merge sort.
Do they do radix sort in it at all?
No, radix sort isn't a comparison-based sorting algorithm.
Well, so if those were all numbers, so if
Yeah.
they were sorting numbers, they could have just done.
Yeah. No, but that's not what they're doing there. So they have, I'm not sure what the name of the algorithm is. It's like a combination of a couple algorithms. Yeah?
So in class 1 you're saying that like the maximum number of like stack frames you can have is like 100-something thousand or 100,000 or so in Java. So with merge sort, wouldn't the number of stack, like as the array gets bigger and bigger, wouldn't you approach that number?
How deep will the recursion go? So if you're sorting a 1,000,000 element array, the first merge sort is going to split it into arrays of size 500,000, and then 250,000, and then whatever. You keep splitting the array in half until you get down to 1. That's how deep the recursion can go. Okay? How many times can you divide 1,000,000 in half before you hit 1? Okay? The answer is about 20. It turns out to be the log base 2 of 1,000,000. That's how you calculate the depth of the recursion. And that's about 20. So you only get 20 stack frames deep sorting a 1,000,000 element array. If you sort a 1,000,000,000 element array, you get 30 stack frames deep. So not a problem. Yeah?
So why doesn't the relearn be more an efficient sorting method instead of just saying these are your top 3 efficient ones? Use these in your program.
The reason you study the less efficient ones first is because they're easier to analyze. So also, even like insertion sort, there's not much to say for selection sort, but insertion sort is really good if the array is already sort of sorted. And a lot of things that occur, sometimes you get something that was sorted originally and now a few things are out of place. Insertion sort's really fast on an array like that. But in a class, you study the less efficient ones just because it's easier to analyze than the more complex ones. Yeah?
What is your array here? Where is that coming from?
I have a method called makeArray that makes an array of a given size. So if I go look at it, it just uses a random number generator to throw integers into an array.
Just a tip. What did you do to follow the method? Just to follow it to whatever.
I right-clicked on it and said open declaration. In fact, it's just F3. You can remember F3. Yeah, you can also open call hierarchy. So I can look at all the places that method is called right there. Although I have to admit, when I need to know all the places the method is called, I change the spelling of the method by 1 letter and look where all the errors are, where all the red marks are. That's just because there's too much to remember about Eclipse. Yeah?
So, quick question. So I was looking into the sorting methods, and they were saying that some were more stable than others, and that Quicksort was by far the most unstable. Is that?
Well, okay, so yeah, Quicksort is not a stable algorithm. But stable doesn't mean incorrect.
Yeah.
It's a technical term which basically means if 2 elements are the same. So imagine you had in your array, you contained a 6 right here and an 8 right, and another 6 over here. A stable sorting algorithm will not interchange these 2 6s. These 2 6s will have the same relative order after the sort than before. And you may wonder why that matters. but usually there's other data associated with the key. So imagine this 6 was Joe's Social Security number, and this one is Judy's. A stable algorithm guarantees that after you sort, Joe will still come before Judy. So ties aren't mixed up. So insertion sort is stable. All right, I got one more thing I want to do. So Stefan's been riding herd on the TAs, trying to get them to pick their favorite animations. And unfortunately, after all that effort, a few TAs never coughed up their favorite animations. So what you're going to see here are the favorites. Stefan picked his favorites from the favorites the TA submitted, but 4/11ths of the class isn't represented. So if you have a fantastic animation and it's not in there, it may be because it just fell through the cracks, and we're sorry about that. But this is, I'm going to show you Stefan's favorites from the ones that he looked at. So this first one is by Alex Barty. And also, I think some of these are compromised by the amount that my screen is blown up, so you might not be able to see all of them. Let's see if I can move this thing up as high as I can. Okay, maybe I should just turn the lights off. Okay, so this doesn't look very promising to start with. I haven't seen most of these.
It doesn't, trust me. The bottom's cut off.
Yeah, so we're not seeing the bottom.
The house is at the bottom real small.
Well, I have to set the screen big enough so you can see the code. Okay. I assume, is there anything at the end to...
No, that's it.
Okay. Cool. Nice job. Okay, this is Jacob Blumquist.
I hope these fit.
Yeah, let's see it.
What?
That's what Stefan was telling me about this one. He's trying to figure out how they did the smoke.
How do you do explosion?
Well, apparently, I don't know if the creator is here, but the smoke is a translucent image that's just being manipulated, rotated.
That's what we're guessing. Haven't looked at.
Okay, this is Adam Drahim. This one I have not seen.
Oh, this is not fitting. You got to fit this to make it. You can't see the legs. That's the best part.
Okay, let's do this. Where do I go to change the...
Displace.
Is it still going to project?
Yeah.
Try again.
It's better, but not. You still can't see the legs.
Is there some way to... How can I drag the window so that it... Oh well. I'll post these and you can look at them. That's too bad you can't see the
It
legs.
looks like something from Star Wars.
It's supposed to be blood shooting up.
Very cool. And the sign of life. All right, sorry about the cutoff. Okay, this is by Spencer Elkington. Spencer?
Yeah.
How do you do this effect?
It was mostly an accident. It wasn't
Great accident.
It was an accident. So it's just a lot of dots that are all manipulated based on how many frames have gone by. So you just use a lot of those spaces to like make it up like that. And then I just overlaid an image because I would have done it by like actually where each dot is.
This is Edward Goob.
This one's using objects, obviously. Objects.
Okay. Then we have Rafi Kwankem. Oh.
This one's cool. 3D.
Yeah. That is neat. And two more. Christian Sandrowski.
You monster.
That's fish food.
Okay. And Steven Sims.
These are not translating to YouTube at all. YouTube's seen about 1/8 of the screen.
Yeah. Okay, Stefan, we need to get the other three TAs to cough up their favorites, and maybe we can do another.
Okay. Hey, I've been begging for a month, for 3 months.
All right, very nice. Congratulations, everyone. We are done.
Did you cut it? Joe.